Hello, I'm here at Electronica 2024, and right now I'm pleased to be joined by Henrik Mannesson, who is the General Manager for WW Grid Infrastructure Industrial Systems at Texas Instruments. And today we're going to be talking about energy infrastructure applications featuring real-time MCUs. So Henrik, thank you very much for joining us. Why don't you give us a bit of an introduction to yourself?
Yeah, first of all, thanks you for having me. It's great to be here. So my name is Henrik Mannesson. As I said, I work for Texas Instruments. I'm doing the systems teams for energy infrastructure, where we are focusing then on end applications like solar, EV charging, energy storage system, smart metering, and so on. So all the large type of energy applications out there.
Fantastic. And I know most of our viewers will be familiar with Texas Instruments, but give us a bit of an introduction to the company as well.
So Texas Instruments is a leading supplier of analog and embedded processing semiconductors. It's been around for a very long time, and especially if you think about the market that I'm coming from and the energy market, obviously TI has been for a very long time in the smart meter business. So that is really the foundation where a lot of the energy, the energy infrastructure market started to turn towards semiconductors. Obviously now, solar, EV charging, energy storage systems are new type of technologies that uses a lot of semiconductors. So that's maybe where we spend most of the focus today from a semiconductor standpoint and our development resources. Yeah.
Now you've mentioned it briefly already, but can you start by telling us about TI's energy infrastructure design resources?
Yeah, so as I said, I lead a systems team. We have about 15 systems engineers on my team. They work mainly with direct, helping customers, realize their designs. So if that's in a smart meter design, if that's an energy storage system, we have a team of system engineering resources. They help. They can go directly to help with customers, maybe that's on hardware or layout issues they might have, but there's also, of course, a lot of work on different type of topologies, helping putting firmware together that then will help customer easier to evaluate your products and so on. And I would say in general, our team very often get involved when there is maybe multiple chips from TI involved, so to say. So instead of some of those applications, they are fairly complex applications. There's a lot of different opportunities for different chip technologies in there. So we need to bring that all together. That's very often where my team gets involved.
And what specific applications can you help with?
So as I said, solar is of course a large and important one for us. Smart metering is also something where we have a lot of resources on. Energy storage system, EV chargers. Those are the large applications really in my field.
Fantastic. And can you tell us more about the TIDA, the 010955 reference design? It's for AI-based arc detection in solar applications. Yeah. So what are its key features?
Yeah, so maybe do a little bit of background to the design and where we're coming from, so to say. So arc detection is an important feature in string inverter applications because it's used on rooftop solar installations in a lot of markets around the world. They require this by UL standards to have an arc detector. Arc detectors has been around for a while. The current methods are, they're fairly good at detecting arcs, but unfortunately also they detect a lot of things that are not arcs, so to say, because there's a lot of disturbances on those lines that comes down, the string inverter line that comes down from the roof down into the string inverter. There's a lot of disturbances that come from, it could be high voltage power switchers that generate noise into those lines. It could also be power line communication that is happening on the same lines, and then at the same time, the impedance of this whole system is changing because of changing conditions of solar, or because of because it's changing the position of the sun, or maybe rain and things like that causes the capacitive coupling to the roof to change. So it's a complex problem to detect those arcs, and that's where machine learning algorithms comes in. So instead of previous methods that then have been very often based on some kind of FFT, so basically you read in a current over a broad frequency band, and then you create an FFT and you start to bin, this data into different frequency bands then. And then you try to set thresholds to say, okay, there's this much energy in this specific band, then that's an arc and this is not an arc. The novelty of this method is really that instead of having to do that manually, you basically let a machine learning algorithm look at a set of arcs, so to say, and then instead that algorithm is going to say what is the where should those levels be in those different bins, and then you take that trained algorithm and you deploy it back onto a microcontroller that sits in the string inverter, and now it's going to operate on arcs any future arcs that this system is going to see. And the novelty of our solution here is also, of course, as well that we then inside that microcontroller, it's a C2000 microcontroller. We name it P55. It's a new generation in that C2000 series of microcontroller, where we have then a small coprocessor that is we call it a neural networking processing unit, or an NPU, that then helps to accelerate those machine learning algorithms. Mm-hmm. So at the end, from a customer standpoint, then you would get low latency, which you want in those type of systems, because if you detect an arc, you want to be able to turn off your systems very quickly. And then the other thing is that you will still do it with very low power consumption, and have not significantly increase the processing requirement.
And I understand that this design is part of an AI-based arc detection toolchain. So what else is included?
Yeah, so the toolchain, when I described the process before, that is the process that you would probably will take if you want to go and develop this yourself. So you would probably have some kind of arcs that you record, and that you could do with an arc generator, or maybe you already have arcs that are recorded, so to say. Now, the first thing you need is to get that data labeled, so that you have then clear data of this is an arc and then this is not an arc, so to say. So now you have created, you have captured the arcs, you have labeled the arcs, and then you're going to go into the next step of training your model and then choose models, so to say. And we offer a couple of example of models in our tool environment. Customers can choose to use them. They can use other models that they might have or might want to explore, so to say. That's all possible in that same tool. So then after that, you're probably going to go and then evaluate which model meets the performance standards that you need, because each and every model is going to have it's going to vary in how accurate it is to detect the arc, but it's also, of course, going to vary in how there is always a trade-off between accuracy and latency, so to say. So you're going to have to pick and choose where you find that's the best system for you.
Yeah, that sounds brilliant. And I'd love to chat about another reference design that you have, which is the TIDA-010938. Get that right the first time.
That's right.
Now, this one is a GaN-based single-phase inverter with energy storage applications. So can you tell us about this one's key features?
Yeah, sure. So in that design, so if the first design we talked about, that's really, it really sits inside this, area of, I would say, current and voltage sensing, which is one important area for many of those end applications that I mentioned before. Now, this is the 938 is really, it's really an example of a reference design that is more targeted toward high voltage power. So in the high voltage power space, there's a lot of things that happens inside that space as well, because of course a lot of those applications that we talked about, solar, energy storage, EV charging, it's all about converting AC to DC or DC to DC or DC to AC. So it's a lot of power conversion going on there. And in this design, we have actually combined a lot of those things into one, into one single design, basically. So we have a DC to DC input that would usually be a string inverter input, so coming from solar panel strings. There's another DC to DC converter inside the design that then can push power or charge or discharge an ESS system, so an energy storage system, where we then can store energy if we're not able to use all of it right now, or we want to store it for later and sell it. And then there is an AC to DC converter inside, or a DC to AC converter. It's actually bidirectional, so both is true. And that can then push power out to the grid, or take power from the grid and use that to charge the energy storage system, for example. Mm-hmm. So it's really those three pieces, so to say, that then brings together solar, energy storage systems, and I would say that the key two features, or the key two areas, or maybe three, where TI and our parts play a role there is. One is we're using one single microcontroller to control all of those power stages. So that's, of course, from just a performance standpoint, it's fairly complex. It's multiple different control loops running in parallel to control all those three power stages. And there we also use a C2000 in the same P55 family that I talked about before. So the nice thing about this is a string inverter type of design. We talked about string inverters before. You can potentially bring this all together into one single microcontroller then. So that's one part of it. The other thing is then really our GaN devices. So that whole system with all those three converter stages, they're all based on GaN devices from us. That then really helps with bringing up the efficiency in the design. Which drives down the losses, that then helps with the thermal performance of the design and give us that high conversion efficiency that we want. And then the last piece of it is really our current and voltage sensing products that we have inside there as well, that then helps us to close all those three control loops. And because TI there have multiple different ways of doing current sensing, for example. We both use Hall-based sensors, we can use shunt-based sensors, they can be isolated, non-isolated. We have solutions for all of that.
What would you say is your primary goal or goals in developing this GaN-based single-phase string inverter design for energy storage?
Yeah, so like I said before, and some of the things that I mentioned, I think what we really wanted to achieve was to show that we will one single microcontroller that we can control, three, complex control stages. We wanted also to make sure that it was done in a way that it's, that it's cost efficient. Then, so obviously using one single microcontroller helps with cost efficiency. But it's also then important, of course, how you implement it, because you can end up with maybe one single microcontroller, but instead you get a lot of, digital isolators, or you need to do, a lot of isolated power supplies instead. So here we really try to, optimize, where we put the microcontroller, so that we can minimize the number of isolation stages we need and isolated power stages we need, so that we overall reach a cost efficiency in the design. So that was one of the main things that we were really looking at. The second thing was really to show efficiency, so to drive up the efficiency over the overall system. And overall, we can reach about 97.5% efficiency from an input stage all the way out to the AC stage. So that's very high and higher than most systems that are on the market today. And remember, this efficiency becomes very important, especially if you think about energy storage systems, because there really you get hit two times because you're going to store in energy, and that's going to create one power conversion, and then you're going to take that energy out again. So if the efficiency is low in that stage, or that conversion stage, you're going to basically get one loss when you convert it in, and then another loss when you convert it out. Yeah. So if you can to just shave off 1% or 0.5%, there actually has a big impact on the overall efficiency of a system like this.
Let's focus on the GaN technology for a minute, and you've mentioned a few points already, but how does using GaN technology help enhance the efficiency and reduce the form factors in this reference design?
Yeah, so obviously GaN, GaN technology, intrinsically, the GaN technology means that we can switch at much higher switching frequencies. So when we switch at high switching frequency, we can drive down the size of inductors and capacitors on that board. And by driving down, and if you look at any of those type of designs, the largest components that are on any of those boards is going to be inductors and capacitors. So if we can drive down the size of them, it's going to have a huge impact on the overall size and weight of this type of equipment. So that's really where our GaN, our GaN devices, we can switch them. In this case here, we use those three different power stations use different switching frequency, but they're all around 100 kilohertz type. So that's quite a lot higher than most systems in this type of application used today. So that's obviously drives down size of inductors, capacitors, and then the other thing to it as well is what I talked about earlier is on the efficiency side, because if we improve the efficiency, that also efficiency, you could turn it around and say that, if you say we have 98% efficiency, it means that there is 2% losses, so to say. So 2% losses in a 10 kilowatt system, that's 200 watts. Those 200 watts needs to be cooled off somewhere. They're going to go into, some kind of thermal or heat sink or something. Of course, if we can make that heat sink smaller, that's also going to have a very big impact on the overall cost and the size of this type of end equipment. So that's maybe the two areas where GaN really helps us.
And how would you say this reference design really aligns with the growing demand for scalable and efficient energy storage systems?
Yeah, so as I said, there is an energy an energy storage port, so to say, so a DC to DC converter that then can take, a bus voltage that we have inside the system. We can convert that down, to a wide range of different type of battery voltages where you're then going to store where the energy is then stored. Mm-hmm. So, I think that's really the part of it, and then we talked a little bit about efficiency before. That's important again for those type of systems. So that's really where how this design supports energy storage systems.
So given everything that you've said, then why should engineers choose TI for their energy infrastructure solutions?
I think there is three different areas where we really could look inside there. I mean, first of all, we have a very large portfolio. As I said earlier, we're a leader in both analog and embedded processing technologies. We have talked about here today. We've talked about actually the three large areas of our portfolio, which is then analog power products where GaN belong, and that's of course a large portfolio that has a lot of other type of products that you might be able to use in those type of designs. That could be isolated power supplies, that could be isolated gate drivers, and so on. And then I talked a little bit about current sensing. So current sensing would be more of a part that from our signal chain portfolio of products, where current sensors is one, but it could also be standard operational amplifiers, ADCs, and so on that you might need in this type of application. And then the C2000 P55 that I talked about, that's part of our embedded processing portfolio, which is one example of a product that we can use here. But maybe also the string inverter wants to be connected to a wireless network. Then we have wireless processors as well, or we might want to run a Linux machine on an energy storage system. And then we have Linux processors as well. So it's really in those three buckets. I think that's an important part of it. The other thing is, of course, we have a large and broad sales team, field application team, resources that can help customers with implementation. So I think that's important as well. And then the last thing is really we want to make it easy for our customers to do business with TI. So we want to help provide the easy way to get our semiconductors. That might be directly through someone like DigiKey. People come through TIA.com and find solutions from TI. So I think those are the three main things that that's going to help us. And maybe lastly, I would say my team, and we can also, help our field application team and, make those designs easier for the customers to use.
Yeah, excellent. And given your experience then, I'd love to hear what emerging technologies you think show the most promise for the future of energy infrastructure.
So I bet walking around, at the show floor here at Electronica the last couple of days as well, I think there is really, three technology areas that I see across, energy storage or, our energy infrastructure systems that are key here. And I think we have touched a little bit on them throughout this interview, but I can go, of course, a little bit more into detail and maybe a little bit what we see moving forward. One would be this high voltage power converter, which with the 10937 is an example of. And there is really, I think, what we see there is a push for increasing efficiency of those power converters. I talked a little bit about how we can make them, smaller, drive down the size of inductors, capacitors, drive down the size of heat sinks because we do them more efficient, so we don't need to waste so much energy into heat. And I think that trend is really going to continue in that high voltage power conversion. And given just that energy systems today, we need a lot of DC to DC, DC to AC conversion. So just the importance of continue that path of improving that. That's definitely a clear trend, and I think that there's still much to be done in that space. The other thing, we haven't talked so much about it, but we talked a little bit about ESS systems. So obviously, the grid is going to need a lot more storage type of systems because the sun is not always shining, the wind is not always blowing. So if you want more renewable energy, we will build more energy storage system. Energy storage systems, the need is really battery management. Batteries management is really a key to control, those large-scale batteries. And that's another area where I know from TI's standpoint we invest a lot to drive technology forward there to make sure that you can use the most amount of power out of those batteries, make them safer to install, and make them more connected to the grid. So that battery management piece, I think, is also something where we will see a lot of development over the next coming years. Mm-hmm. And then really the last thing is what we gave an example of here was this AI-based, current sensing in some way. We call it arc detection here, but I think if we think about that space in a little bit of a broader context, I believe that anytime in any of those systems we measure a voltage or a current or a temperature or whatever that is, that tells us something about the state, or gives us actually more information than we're able to use than we're able to extract or use today. But then with help of those machine learning algorithms and so on, I think they're going to be applied to a lot of those voltage, current, temperature sensors, where we're then going to use that information, extract a lot more information about how the health or build safer systems based on that. That I also see as a big trend, and where I think the TI and the market's going to continue to push towards.
Do you think AI has got a big role to play in the future of the energy market?
Yeah, I believe, obviously, I think on a high level, yes, in the sense that, to control all of those energy resources, there's going to be a lot more energy sources out there. So to be able to make good predictions of, wind, solar, storage resources, and so on, AI, of course, has a role to play there. But that I would see more as a cloud AI type of solution. But I really think that where Texas Instruments is focused on is a lot of that what we call edge AI, where we're trying to put AI or machine learning algorithms very close to where we then measure any of those voltage or currents or temperatures or wherever it is. And we do that because they may be safety relevant, as the example with arc detectors, but they could also be reasons for other reasons that we need low latency. We have very little. We have a low processing power in many of those edge nodes, so we don't have so much power in all of those edge nodes. So there, you are obviously then going to need microcontrollers and so on, and microprocessors with AI or machine learning algorithm accelerators to be able to deploy those type of algorithms very close to where we measure voltage, currents, temperatures.
Well, it's certainly a very exciting space to be working in at the minute, yeah. Okay, so before we wrap up then, why don't you tell us a bit about your partnership with DigiKey and how you see that benefiting your customers?
Yeah, so DigiKey, I mean, we see them as an important partner for us when it comes to, I think for just getting products, so to say. So people come to your webpage, they search for products, they find TI's complete portfolio of products in DigiKey. And that's great. You then also help with getting samples or parts to the customers fast and easy. You can also, I think also that there is a vibrant community of people that interact with with the forums and other web web type of collaboration tools on DigiKey's pages. And of course, if TI's solutions are present there, that's great for us. So and that's really where I see DigiKey is helping us.
Excellent, thank you. Well, it's been a real pleasure listening to your insights, and thank you for sharing the information about what TI is doing in the energy infrastructure business. So thank you very much.
Thank you. It's been great to be here.